The TBS1000B and TBS1000B-EDU series offers flexible triggering alternatives to help you capture and characterize digital signals. Capturing the right digital event on an oscilloscope can be challenging. However, with a few simple techniques, the TBS1000B can help you get a stable display to get good measurements, and they can also help you capture data packets and intermittent events like glitches and dropouts. The easiest type of signal to trigger on is a periodic one, like a clock. Let's look at a clock signal with frequency of 20 MHz and amplitude of 4 volts. In general, pressing Autoset is a good first step toward getting a stable waveform, especially for periodic signals. On the TBS1000B, the Autoset feature lets you quickly access views of rising and falling edges, or single clock cycle of the clock by pressing the soft keys associated with the menu items on the right of the screen. Most of the TBS1000B oscilloscope features are accessed this way. The Autoset function has automatically configured the trigger. Let's take this opportunity to review the trigger controls. In addition to edge triggering, the TBS1000B also has pulse and video triggering options. We'll talk about pulse triggering a little later. The slope control is set so that the scope triggers when the signal is going from low to high, that is, a rising slope. Auto mode lets the acquisition free run. The scope will trigger periodically even if the trigger conditions are not met. This is the default, and it's a good place to start while you're getting the settings nailed down. Normal mode only updates when the trigger conditions have been met. Trigger coupling lets you apply filters and hysteresis to the trigger signal. For digital signals with well-defined edges, you probably won't have to worry about this. The trigger hold-off lets you set an amount of time where additional trigger events are ignored after the initial trigger. Now let's take a look at a single-shot event. Let's say you want to look at the clock as it starts up. To watch the clock start up, the triggering is set to trigger the first time it sees a rising edge that passes through about 2.2 volts. Now let's use single shot to see the clock starting up. First, I'll set the scope to capture a single shot event. Then I'll start the clock. The scope captures the first cycle of the clock that goes above 2.2 volts. Digital signals are seldom simple periodic pulses. Pulse trains and bursts make up the data, address, and control signals. Let's take a look at some more typical digital signals. An easy way to get a look at any signal is to stop the acquisition. Once you stop the acquisition, you can use the horizontal controls to look at signal details. This is easy to do, but you only get to see a handful of transitions. To get a more dynamic picture of the digital signal, you can change the horizontal scale to acquire more data points and then use the magnifier controls to see more details. You can zoom in by up to 10 times the normal view and position the zoom window to any point on the waveform. Often, digital data comes in packets. Simple edge triggering won't allow you to pick out the packets. You can use pulse width triggering to capture them. Let's take a look at some I2C information. We'll set the scope up to look for idle time in between clock bursts. I'll press Autoset to get started. The waveforms show up, but they're not very stable. To trigger on a packet, we'll use pulse width triggering to capture whenever the clock is idle for more than 100 microseconds, as it is at the beginning of most of the packets. I'll set the scope to capture a positive pulse greater than 100 microseconds. By using pulse width triggering, I'm able to consistently capture signal information that occurs at the beginning of packets. Pulse width triggering can also be useful for triggering narrow pulses, like glitches. After an Autoset, these pulses look just fine. The narrow pulses look to be around 100 nanoseconds in duration. But there's something lurking below the surface. It doesn't show up because it occurs so infrequently. We can set the scope to capture any positive pulse that's less than around 80 nanoseconds long. The scope captures a pulse with a glitch on the leading edge. Thanks to pulse width triggering, we can get a good look at the event. Now you can see how to use the TBS1000B or TBS1000B-EDU oscilloscopes to capture your own clocks, data, packets, and if you need to, even glitches.
Find out more at Vicom's website.